Let's start the session. My name is Naomi Chatano. I'm chairing the two people. So the first speaker is Chihiro Matsui from Department of Mathematics of University of Tokyo. She's going to tell us about the variety of partially solvable models, from closed spin chains to open spin chains. Please.
Maybe microphone. Yes. So let's use this. Sorry. But it's not turned on. Then I guess.
Okay. Sorry for different thing. First of all, I'd like to thank the organizers giving me an opportunity to give this very exciting workshops. Today, I'd like to talk about partial solvability for both closed and open spin chain. So this talk is based on collaboration work with Hosho Katsura, who is one of the organizers of this very nice workshop, and two mathematical physicists, Chiara Paoletta in Ljubljana and Balázs Portugal in Budapest, and Naoto Tsuji, who is a condensed physicist. So I myself is a mathematical physicist, but I really want to share our knowledge with the people from various backgrounds. So if you find something unclear, don't hesitate to ask me at any time. Okay? So this is the outline of my talk. First, I will define what partial solvability in this talk is, and then explain the relation to the summarization phenomena and the emergence of quantum manipulated scars, which was already discussed in several talks and also in several posters. And then I will show several examples of partially solvable models for closed quantum systems and open quantum systems. In this talk, I will deal with totally 4 different kinds of models. So don't be confused. I try to maximize my time, but if you get lost, please tell me. Okay. So, do you imagine from the word quantum inequality? So actually, there is no clear definition. Somebody says that quantum integrability should be characterized by the existence of many enough local constant charges. And somebody says the quantum integrability should be the word which is used for the quantum system with completely solvable energy eigenvectors. So here I want to say the quantum system is integrable if there exists mathematical structure called the Yang-Maxwell equation. So if you are not familiar with the Yang-Maxwell equations, you can just think of many grid scatterings, which you can decompose into a sequence of 2 grid scattering in various space. And then Yang-Maxwell equations guarantee that these decompositions are physically equivalent. Okay. So actually, Yang-Maxwell equation is a sufficient condition for the quantum system to have many constant charges. Because they produce a commuting family of zero-sum matrices, which contains 1 free parameter, and then we can expand this graph matrix with respect to this free parameter, and then we get commuting family of operators. But I don't explain the detail because I don't use it now. Okay. So actually, integrable system, quantum integral systems has been studied for a long time. It has been discovered that there is a very nice, beautiful mathematical structure behind models, and then we can compute everything, including differential functions, by using this mathematical structure. And also in relation to the various kinds of topics, including conformal field theory, has been discovered. But very recently, quantum integrable system has been reapplied in the context of statistical mechanics because they are the typical examples of exceptional quantum systems which never sum up. Okay, probably there should be some various kinds of discussion, but I guess many people now believe that the summarization is explained by the eigenstate summarization hypothesis, which has been already explained in several talks. And the statement is, all the energy eigenstate cannot be distinguished from the summary statement typically in the strong versions. And actually in the quantum integrable systems, there exist the energy eigenstate, which can be distinguished from the summary state macroscopically. So the quantum integral system violates the statement, the strong statement of the eigenstate summation hypothesis. Okay. So with this background, it is very interesting to ask what will happen if we embed the integrability or solvability to non-integrals. This is motivation to consider partially solvable models. Okay. So here I say the system has partially solvable model, has partial solvability. It is Hamiltonian, a relatively small solvable invariant subspace and large unsolvable invariant subspace. So the partially solvable Hamiltonian has this block diagonal structure consisting of the solvable subspace and unsolvable subspace. So actually, there are several methods to reduce the Hamiltonian with this block diagonal structure. So here I listed the three famous methods: projectile embedding, restricted spectral generating algebra, and the fluid space computation. So here I don't restrict the solvability to the integrability. Actually, these two methods usually produces the partial solvability, which is not based on the MX.
So do you impose any condition on the size of W as a function of the system?
Yes, it should be negligible.
So some sub volume.
Yes.
That's the only constraint.
Okay. So before going to the construction of partially solvable models, let me explain a little bit about the phenomenological aspects of the model. So if we prepare the initial state in this small subspace, then this state cannot move out from this small subspace during time operations, because it's completely isolated from the others. Then the partially solvable models weakly violate the ergodicity in the theoretic space. So people believe that the notion of partial solvability is somehow related to the emergence of quantum mechanical discourse, the exceptional energy eigenstate of non-integral systems, which violate the strong statement of energy eigenstate simulation hypothesis. So if you are not familiar to the quantum mechanical discourse, you can just think of a variable moving on the oval stadium. If the ball starts to move from the J point, then it moves ergodically in such a way that covers all the regions in the stadium. But if the ball starts to move from near unstable periodic trajectories, then its movement is restricted to a very small region in the stadium. So this is a typical example of weak violation of spatial ergodicity for single body classical systems. And a similar weak violation of ergodicity can be observed in the Hilbert space for the quantum many-body system. And we say this exceptional state as quantum many-body systems. Okay? So of course, it is not easy to say whether the state is really someone or not, unless we are working with integral systems. And usually, the quantum many-body discourse shows up in the non-integral system, so it is very difficult to compute everything. But there exists some signs which say the state is quantum many-body discourse. The first one is persistent oscillations, which is observed in the expectation value of local observable. So if there exists long-lived oscillations, we can conclude that the state never survives. We can even say that the state never reaches to the realization state. The second one is relatively small entanglement entropies compared to the thermal state, which usually has entanglement entropies obeys the volume law. So here you can see the dots completely separated from the thermal state, and they are actually quantum mechanical discourse, which have a small entanglement entropies, usually obeying some volume law. So this fact strongly motivates us to look for quantum mechanical discourse in the expression of matrix product state with finite quantum dimensions, because they usually have a small entanglement entropies. Right. And here you can also see that this quantum many-body scars are spaced with equal intervals in the energy directions. And this explains the emergence of persistent distributions, which we just saw in the previous slide. Yes, and I will come back to this point very soon. Is there any questions?
Actually, I have a question. So, you said this quantum, you presume or assume that this quantum many-body scar may be a matrix product states. What are the other possibilities?
I'm not sure.
Okay.
So I want to move to a concrete example. So what is for closed quantum systems? Okay, so I'd like to show the partially solvable induced by the restricted spectrum generating. So the restricted spectrum generating algebra. So we say the Hamiltonian has the restricted spectrum generating algebra if there exists a local operator, which is usually the situation operator of space-time property, which satisfies this dynamic symmetry. So the local operator that does not commit with the Hamiltonian even in this small subspace, but comes back to each side with some prefactor. And actually this prefactor determines the energy intervals in the solvable subspace, because once we find a solvable energy eigenstate, then we can create the other energy eigenstate by applying local operators to this obvious energy eigenstate. And all these have different eigenenergies, but with equally spaced fruits in general is just determined by this prefactor. Okay? And this practically explains the emergence of long-life situation. Of course, we have the initial state prepared in this solvable subspace, and then the time evolution of local operators can be expressed by these expressions, which exhibit the oscillations whose frequencies precisely given by these prefactors. Okay? Indeed, if we compute the evolution echo for the model which exhibit the restricted spectrum generating algebra, then we see the strong variables in its dynamics as long as the initial state has strong overlap or large overlap with this solvable subspace. Okay? So, where can we observe spectrum generating algebra? So, spectrum generating algebra already shows up in the regular model, simplest model for physicists. So, the Hamiltonian Flickr model is simply given by this binary expression. And then, so here you can see I wrote everything in the momentum space. And then it is easy to see that this permutation operators does not fit with the Hamiltonian, but comes back to itself with some, which depends on the momentum of the fermions. Of course, here we don't have square of fermions and power of fermions because it's fermion. But anyway, we can construct the exactly solvable energy eigenstate on the top of the anchor state, which is the vacuum in this case, just by applying the Fermi operator to this anchor state. Okay? So this is a completely solvable case. And the similar thing can happen only in the small subspace of the Hilbert space for certain kinds of models. The simplest example is perturbed spin 1 exponent. The Hamiltonian is simply given by the x-y interaction between spin 1 spins and magnetic field in the z directions, which is the reason why I say the model is perturbed. So actually, this is non-integrable models with spin 1. So not all of the energy eigenstates can be solvable, but we can easily find the trivial energy eigenstate, which is just given by the fully polarized state, all the up or all the down, which I choose as the anchor state for this model. And then there exists the other energy eigenstate, which can be exactly slower. And they are expressed in terms of the specific particle expression. So here, quasi particles are spin two magnet, which carries momentum phi, and these quasi particles are created by these ratio operators, and these ratio operators satisfy the restricted spectrum type, generating the object in subspace of this quasi particle excitation state. Then we get the equally spaced spectrum in this sort of subspace, and then we again observe the emergence of long-lived oscillations, which perfectly match the phenomenological evidence. Okay, so this is the simplest case. So,
when you restrict to the subalgebra, you need to choose a projector, right? So, or the basis of W curve. What is the choice?
choice is
just explicit there.
This is just an explicit construction. I accidentally find the obvious energy eigenstate and then subsequently apply this operator, then create some space which is equivalent to
the meaning of the projection, but it's
the assumption.
yes, okay.
Inside this campus.
This algebra is satisfied only in this subspace. And then go to space. Okay. So the other example, the athletic delivered model, is a little bit more. So here I want to use a little bit deformed version like a model just for generalizations. But if you really want to use AKLT, original AKLT model, you can just contain this way and you look up as original AKLT. But again, spin one non-integral spin chain, so not all of the energy eigenstates are solvable. But for some reasons, people from the old times, people know that the ground state and the single excitation state can be exactly solvable. But people didn't know why they are solvable, at least at the algebraic level, for a long time. But now we can understand solvability from the viewpoint of the restricted spectrum generating algebra. Okay. So the zero energy eigenstate of a GLK model is usually expressed by matrix state. So here I prefer using this storage notation. So vector A is the matrix of the vectors with three components, each of which is given by 2 by 2 power matrices. And K here is again the 2 by 2 matrix, which acts only on the auxiliary space. And this K is actually determined by boundary conditions. So K is chosen to be an identity for periodic boundaries, and K must be some matrix with rank 1 for open boundary condition. Okay. The reason why this matrix product state provides the zero energy eigenstate of a GLK is understood by these local relations, which we call local divergence condition or translation-free condition. So if we make a summation over all the sides, then we get 0 on the right-hand side if we impose the boundary periodic boundaries, which implies this matrix product state is indeed zero energy eigenstate of the extension. Besides this zero energy eigenstate given by matrix state, there exists a tower of solvable energy eigenstate, which is again described by quasi particles. Quasi particle here, again, spin two magnets carrying momentum back, and the statement is a state which is created by applying this relation operator to the matrix product state, again provides the energy eigenstate of the AKLT model. Okay. So here I denote that here I replace the vector A at the position of the quasi particle with vector B, which I just observed or obtained by applying this plus K operator to the original vector A. And this statement is verified by these local relations, which I call the local eigenvalue conditions, and refers to the property of quasi particles which forbid the adjacent or double operation. Okay. So it is not really clear what is happening there from these local conditions, But actually, these local conditions are equivalent to the emergence of restricted spectrum generating algebra in the subspace spanned by the quasi-particular state. So the APLT Hamiltonian satisfies restricted spectrum generating algebra in the subspace of the quasi-particular state. So this is the reason why this is solvable, partially solvable. Okay.
Is it necessary to go to MPS picture to do this?
Well, yeah.
Is it essential to have MPS?
In this construction, I would say it's essential. Now, for the internal knowledge necessary. And anyway, we need one anchor state, which should be some.
Okay.
Yeah,
In this case, you started from MPS, so you're.
And the strange thing is the MPS state here is not really vacuum of this quasi particles. This is very strange. But anyway, this is another story. Talk about, right? And then, okay, so now we have this restricted spectrum generating algebra. We again get the equal spaced spectrum in sort of a subspace, and then we will see the emergence of long-lived expressions. This is good, but what is frustrating for me is all these particles are identical and non-interacting. This is not really interesting in the physics sense. Okay. So what I want to do is what I want to ask is what will happen if I replace the momentum of each quasi particle with the arbitrary one and let them interact with each other. When these informations, we lost one of the recursive property of this quasi particle. So the adjacent occupation is still prohibited, but double occupation is not allowed. So what will happen in this case? We have some partial solvability for the model. And the answer is actually yes, but the model is of course equal. So here I want to consider these models, which I call the portable XXC model. The Hamiltonian consists of the two parts. The first part is just XXC interactions, which is irregular, and then I add some perturbations, diagonal perturbations, which breaks integrability of the model. Then what I have found is this quasi particle excitation state provides the energy eigenstate of the perturbed XXC models as long as the momentum of quasi particles satisfies beta equation for the spin 1/2 XXX model. This is rather strange because I'm working on spin 1 chain and then I got the beta equation for the spin 1/2 XXX model, right? So what's happening there? Okay, so if we regard the vector A as up spin and vector B is just down spins, then this particle state really looks like the beta state for the spin 1/2 X chain. Right? Then I would like to consider the action of the Hamiltonian on this space, which is spanned by these two bases. Then what we get is really the action of the Hamiltonian for the spin 1/2 XXX chains as long as we stay in the subspace spanned by this strange quasi particle state. Okay? And then we of course get the energy spectrum which completely matches the energy spectrum of the spin 1/2 XXX model, except for its degeneracy. Okay? So this is rather strange, and I really don't know what is the mathematical structure behind these models, and I even don't know what is the algebraic relation satisfied by the equation operator of this basic particles. But actually, the partial solvability of this model is understood by Hilbert space fragmentation, which was just explained in the previous talks. So it's nice. But here I want to replace the Hilbert space fragmentations in the spin-chain language because I'm dealing with spin-chain. So the Hilbert space fragmentation is characterized by the exponentially many block diagonal structures. But it can happen that Hamiltonian have exponentially many block diagonal structures because of the existence of local symmetry of the Hamiltonian, such as total magnetization. And in this case, we want to say the Hamiltonian exhibits a Hilbert space fragmentation. Say the Hamiltonian has Hilbert space fragmentation structures if this fragmentation is brought by non-local symmetry or symmetry. Okay? The Hilbert space fragmentation itself is not necessarily related to the notion of probabilities, but it is sometimes possible to embed one or several subspaces, embed integrability of probability to one or several subspaces. Okay? So I want to show several examples which exhibit Hilbert space fragmentation. The simplest example is the Sato's model. So this is non-integrable spin S feature. So we cannot derive all the energy eigenstate exactly. But if we look at the Hamiltonians very carefully, we may notice that the interactions in the exchanges neighboring configuration. So for instance, if we apply Hamiltonians to this initial state, then we get totally 5 different configurations after the action of Hamiltonians, but they are obtained just by replacing the neighboring configuration. But this also means that the Hamiltonian never changes the number of each entries in the initial state. That is, the Hilbert space is fragmented according to the large set of configuration entries. Okay? So this is a simplest example which exhibits the Hilbert space. What's interesting for this model is Sato's model can be integral in several subspaces. Suppose we choose 2 species out of 2s plus 1 species of the spin S chain, then the action of Hamiltonian restricted to the subspace found by these 2 species is exactly the Hamiltonian of the spin for the spin 1 of the XXZ model, by identifying what species with upper spin and the other one with downspin. In this case, the anisotropy depends on the choice of the species. So the Sato model is somehow a combination of various kinds of XXZ species with spin 1 half with different anisotropies. Okay. The example has a little bit more complicated descriptions. So this is the XXZ model. So this is the before the formation of my model. So actually, it is known that the XXZ model is the integral model. So in the sense that there exists a matrix which solves the above equation, but you can just imagine the integrability of these models by identifying the states 0 and 2 out of 3 states of spin 1, 0, 1, 2. And then we get the spin 1 half XXZ Hamiltonian, which is, of course, we know integral. Okay. If we carefully look at the interaction of this Hamiltonian, then we notice that the first part just provides the diagonal interactions, and the second part is the exchanging terms, consists of the exchanging terms, but these terms exchange only the states 0 and 2, 0 and 1, or 2 and 1, but never exchanges the states 0 and 2. Okay? And this means the partial configuration consisting of 0 and 2 completely frozen by the action of Hamiltonian. This we call irreducible strings. Okay, I want to show some example. So, for instance, we have this initial state, then we can apply the Hamiltonian to this initial state. Then we get totally 6 different terms with different configurations. But you can see if we neglect all the ones from each of the states, then we always get the same configuration consisting of 0 and 2, 0, 2, 0, 2 in this case. So this means the configuration of 0 and 2 is completely frozen by Hamiltonian, which we call irreducible strings. So now I want to violate the integrability of this model. So I want to add some perturbations which violate the integrability. The first perturbation I want to consider is this expression. So this perturbation actually violates the integrability of the models, but we know that the same model exhibits Hilbert space implementation. So if we restrict our solver to the subspace and characterized by just between 0, or 2, which we call the fully polarized state, then this perturbation acts as 0 because the configuration 0, 2, or 2, 0 dimensions of subspace. This means this perturbation violates the integrability in the entire Hilbert space, but keeps the integrability in subspace specified by fully polarized subspace utilization constraints. Okay? The similar thing can be discussed for the other sectors. Suppose we have another perturbation, which is given with this expression, then this violates integrability in the entire Hilbert space, but keeps the integrabilities in the subspace specified with alternating reduced strings, which is given by 0202 or 2020, because no sequence of zeros or twos shows up in this subspace. Okay? So this perturbation always acts in subspace, which means this violates the integrability in the entire Hilbert space, but keeps the integrability in subspace, including reduced strings. Let me remark that these two terms are very interesting terms because they not only violate the integrability in the entire Hilbert space, but also violate the Hilbert space computations. Of course, they keep the subspace specified by alternating reducible strings to be isolated, but they mix all the others. For instance, if we meet the sequence of 2, then we get the sequence of zeros, which already belong to a different subspace. And in this way, these two terms mixes all the subspaces except for the subspace of the alternating reducible string. And this is very interesting. So in this way, we can add some perturbations which violate the integrability in the entire Hilbert space, but keeps integrability in a selected subspace. And what is the most important thing is we can keep the integrability in the selected subspace even by adding this kind of perturbation cycle dependently. So I want to use this idea to produce a partial solvability control system. Now, what the system I want to consider obeys linear mathematical equation. The linear mathematical equation consists of two parts. The first one is the time evaluation by the system Hamiltonian, and the second one describes time evaluation by its interaction with the environment. So this is the most general, completely positive and preserving map and the assumptions of Markovian time evaluation of direct product initial speed. And of course, the physical derivation is not so easy, and we need some various kind of assumption. But I want to start from this setup. Okay. The solvability of the Liouvillean has been discussed for various models. So for instance, the complete solvability of the Liouvillean can be discussed for models which is for the Liouvillean with translation invariance, and the partial solvability is also discussed for the Liouvillean with translation invariance. In these cases, these figures are coupled to all the cycles of the system, and they must be all the same. If the system is coupled to the dispatchers only at the boundaries, which I believe experimentally very difficult, then only the steady state is known to be solvable in certain cases. So the motivation of this map is to extend the partial solvability to the open quadrant system, which is coupled to the dispatcher only at the boundaries in such a way that has exactly solvable eigenpoints besides the steady state. And we are especially interested in the case in which the solvability of the Liouvillean, partial solvability of the Liouvillean is inherited from the partial solvability of the system Hamiltonian. Is the cellular subspace of the system Hamiltonian is not broken by adding boundary dispaters. Okay. So this is the motivation of the partial solid region, or studying partial solid regions. So is there any questions? So now I close the quantum system. So now I go to the system. Do you have some questions about the quantum system part? Okay. Okay, so system I want to consider is like this. The system is coupled to this figure than the boundary. So rather than working directly on sensing matrix, I'd like to work on the download qubit space, which is called Choi isomer. This means the previous. So in this, by this I found the this matrix can be expressed by the vectors in the download qubit space, and the action of the Liouville can be expressed by the non-emission Hamiltonian. This is just because of technical reasons. And then I want to set the spin 1 XXC Hamiltonian as well. So we know that XXC Hamiltonian exhibits qubit space representation. And then we set the boundary dispaters in such a way that dogs the up spins and down spins produce both the ends of the spin channel. Then what we get is the action of the Liouville is equivalent to the non-emission Hamiltonian, which is given by just XXC Hamiltonian on a link with double the size, but with different interaction at the boundaries because of the effect of the dispaters.
Sorry, question. So the jump operators do not come in here?
You use the microphone? Sorry.
During as I express this situation.
Yeah, but you are describing this by a non-Hermitian Hamiltonian. So I was wondering if the jump operators change that at some point.
Yes, this is we have only boundary dispaters, only two targets. So
okay.
So this is how it acts, how they act. So this is the boundary dispaters. This is the non-elevation part. And we may notice that the two terms actually act as zero in the subspace of the native reduced string because there is no configuration of twos with zeros, so they always act as zero. So in the subspace of the alternating reduced strings, the effective Hamiltonian becomes two decoupled XXC spin chains, but with the boundary magnetic field. Okay. So only these four terms remain, and the part two terms disappears in subspace. Okay. And if this boundary magnetic field provides the integral boundary conditions for the XXC spin chains by choosing the boundary dispaters in such a way that stops the up spins and down spins with the same point. Okay. We have completely integral spin chains in the subspace of alternating irreducible strings. So with these conditions, we get integral spin chains in subspace of alternating irreducible strings, and then we can calculate everything by beta MZ, either directly working on the XXC spin chain or by mapping the Liouvilleans onto the XXC spin chains with spin 1/2 by identifying the spin states 0 and 2. In this case, the boundary magnetic fields are completely pure imaginary magnetic field, but anyway, we can apply the tendency method using the diagonal matrix. Okay. So, of course, the Liouville itself is not completely solvable, so there are quite a lot of energies of the Liouvilleans which cannot be analytically accessible. Only the spectrum, which is marked with red triangle, can be analytically accessible, which include one a steady state at several degenerate steady state of the level. Okay. So now we have partially solvable open quantum spin chains based on theoretic space fragmentation. And this can be mapped to the spin 1/2 because this spin chains, this is nice because we can do everything, essentially everything on spin 1/2 x this spin chains if there's a presence of only magnetic field. This is very nice. But there are the other way to produce the partial solvabilities for the open quantums. Okay.
So what you're saying is that you have a lot of degenerate steady states, right? But one of them belongs to the solvable subspace. Can you get the other steady states in closed form?
Closed form, yes. Yes, but by different reasons. So for instance, we use the matrix product of the symmetries. I can produce root of a steady state, but a little bit more. Not all, I see. Maybe all. I didn't check it. I have some more. But this does not belong to scientific sectors in this sense.
So in each subspace, is the steady state just like a completely mixed state? Is that something about all the projections?
Actually, steady state in the integral subspace is not a mixed state. It's just simply given by a product state. But
I see.
But if I use the other methods, which I call the matrix product operator symmetries, then I will get some mixed state of the steady state.
So, do you have any non-trivial steady state which has, non-trivial entanglement structure?
Well, not in this integral section, but in the other sections, yes.
Thank you.
Okay, so now I switch to the open, partially solvable open system induced by restricted spectrum generating algebra. So now I want to set the Hamiltonian which is equipped with restricted spectrum generating algebra and set the boundary spectrum in such a way that the precise particles from both ends of the spin chain. So we expect the steady state is naively given by fully occupied state because precise particles coming into the system from both ends of the spin chain. But what we have found is that this is not always the case for this model. This is very strange. And now I want to use the spin 1 AKLT model for the value. And we know that this Hamiltonian has the ground state given much expressions I explained. But in this case, spin chain is open spin chain, so we need to replace a trace with the boundary vectors which lives in the two-dimensional linear space. And we have actually co-degenerate zero energy eigenstate because of the choice of the boundary vectors coming from the speed 1/2 degree of freedom of charges. So it's related to the emergence. So it's fast flags. Okay. And then we can construct a solvable tower of exactly solvable energy eigenstate on top of each of these four degenerated ground states. And what we have found is only one tower out of these four degenerated towers consists of the state which is completely vanished by the action of these vectors. That is, this specific tower consists of the dark state. So these vectors are completely irrelevant in this specific tower. Okay. For this reason, if we choose any kind of diagonal density matrix from this specific tower, this always provides a steady state because it commutes with the Hamiltonians because it is energy eigenstate which vanishes by the action of these vectors. Okay? And of course, this arbitrarily chosen diagonal density matrix is not necessarily fully void state or fully occupied state. Indeed, if we compute the ratio of the number of trajectories each magnetization, we see that the state with small sd immediately decayed by time if there is no overlap between the initial state and discovered. But if there is the overlap, the state with small sd can survive for a long time. Okay? So if there is an overlap between the initial state and this special towers, there exists some special non-trivial steady state which is not given by fully ordered state. And the other stuff is like if we choose the off-diagonal element from this tower, then it does not commute with Hamiltonians because it is not energizing set anymore, but satisfies the restricted spectrum generating algebra with Hamiltonian. And of course, we choose this off-diagonal element from this specific tower. So this is given by the axiom of these figures. Then we get the only remaining thing is this restricted spectrum generating algebra. This means we will see the emergence of long-lived oscillations in the expectation value of the which indeed can be obtained by numerical calculations. So if there exists the overlap between the initial state and these specific numbers, we see the emergence of long-lived oscillations in the local observable, which is SZ in this case, but there is no oscillations if there is no overlap between the initial state and this time. Okay. So, in conclusion, so I have discussed the partial solvability for isolated system and open quantum system. And we have found that the partial solvability of the system Hamiltonian, closed Hamiltonians, can survive even by adding boundary dissipations if we properly choose the boundary dissipators and the solvable subspaces. And for okay, so if this partially solvable, if this solvable subspace comes from the restricted spectrum generating algebra, I have shown that there exists a non-trivial steady state. And sometimes, if we choose the initial state in such a way that have the overlap with this solvable specific power, then the initial state never reaches to the relaxation state by exhibiting persistent oscillations. And in the virtual graphs, what's interesting for me is I expect the emergence of KPZ universality class for partially solvable open systems because this is very interesting because the KPZ universality class is usually discussed for the closed spin-chains, but actually we get the closed XX spin half XX this spin-chain in which the KPZ universality class is expected to emerge, although we are working on system. This is a very interesting feature. And from the mathematical physics aspects, it is of course very important to understand what is the algebraic structure behind the XXC and related models. And I'm also interested in what are the quantities behind the partially solvable models and how it affects on some dynamic of this partially solvable model. Oh, that's all. Thank you.
Yeah. Okay, questions?
Yeah, thanks for the painful talk. In the original quantum many-body scar system, this PXP model, there is a thing that is like approximately your restricted algebra, but it's not quite exactly that case. So can you say something about that, or is that completely out of scope?
I didn't do much about the experience, but
I guess the energy spacing of these states is not exactly equal, right?
The experience. The thinking about the extension to the open system or some other stuff for the closed spin-chain as a closed model.
Well, your whole notion, for example, of having this integrable subspace, I guess that's not happening there.
Yeah, algebra is not closed.
Should be some subspace which is called because it's not for written.
Yeah, it's not exact, right? So somehow I guess you leak into the rest of Hilbert space.
It's approximately closed, not completely closed. No, so that's
Yeah, thank you.
And
very much very interesting. So yeah. So could I understand the Howard model and some spectrum so such kind so yeah so yeah so as the this RSJ. This structure looks very much like the carrying from Howard model. Yeah, so yeah, then maybe my question is, so could it generalize the result to the even higher dimensional case? I mean, yeah, in higher dimensional case, exact result may not exist, but you can construct some subspace due to the spectrum generating out.
Well, I think that's impossible for the interperiod between even for the open regions by accepting like the dispatchers, like the difference dispatchers for all sides of the system. But I'm not sure about, for instance, for the AQT model because it's already very difficult to find the alpha state of higher dimension case, right?
I see. Fine. Okay.
So you discussed the deformation of the XXC model, which has an interesting feature. So how do you find it, or is there a systematic way to analyze? Like I wonder, like if I go back home and then don't have the slide and try to reproduce the deformation, what is the principle?
So this is a starting point, and then I solve this equation.
So you work in MPS.
And then I use the solutions. I accidentally got the solutions, but of course there is no guarantee that there exist solutions.
Yeah, I see. So then I wonder, for example, you can go to other models, like you replace XXC by higher spin.
Yeah, exactly. It might have like
I see. But then why is you know the structure of the APS? Writing that APS is hard. Is that the hard part, or maybe it's just technically complicated, or any obstruction you try to generalize or in the principle?
Say, for instance, if start from the product state and the anchor state, I think I don't have this kind of structure. It's too simple.
So yeah, for this So yeah, for this particular model, there is a better way to understand the relation between XXC and XXC. That is the kind of non-invertible symmetry between these two models.
Okay.
Yeah, I can explain to you later.
I see. It's interesting principle. Then I can ask the QFT question too. Like you can pick a couple sign model and from the deformations and try to to have QFT counterparts.
We can do the similar thing for the XXC models, but I'm not sure whether there exists this kind of matrix expression. So this is actually not really simple expressions, but like, okay, so of course, like 16 models in different models, so we can construct everything in the analytic way. But this is the combination of every descendant. So it has the same energy eigenvalues, but it mixes everything together. So it's great.
Thank you. I'm curious. I have a question to Hosha. So this non-invertible symmetry, it makes use of MPS representation, or it's directly works out?
There is no relationship.
Yeah. And then my point is just the relation between two different.
Okay. Just to kind of. Yeah. My question is, so you have these beautiful structures for these models. But do these long-lived oscillations survive if you perturb the Newtonian? I don't know. So you have this long-lived oscillation coming from this kind of tower structure.
And you think
I don't have because the spectrum in the form of subspace matches XX functions.
yes, of course, I know that this should break down, but but I don't know numerically or not. I mean, do you expect this to be robust? Because experimentalists claim to have observed these scar structures and so on. So to be experimentally observable, they should be robust. I'm curious if these guys are robust. And
Well, I don't have a restricted structure for this model, and of course, I expect a continuous spectrum with some dynamic limit. So I don't think. So I think it depends on the definition of quantum mechanical scars. If you expect something for the emergence of Lie variable for quantum mechanical scars, I won't say this is quantum mechanical scars.
okay, thank you again. Thank you.
So in your final slide, you made an interesting comment on the possible relevance to the KPZ universality class.
Yes.
But in the literature, we of course know a kind of some non-Hermitian models that belong to the KPZ universality class. So that I failed to catch your point. So I want to, for example, propose a new model, or
I don't know. I just didn't know the emergence of KPZ for the quantum non-Hermitian model. So I know KPZ is very locus universality classical based, but I even didn't use KPZ. It's really universality because it's very sensitive to the choice of initial conditions. So I'm not sure about this. But
the famous example is just a ferromagnetic Heisenberg model with asymmetric hopping. Then it gives a KPZ universality class. It's just an AZ model.
okay. So well, I didn't know. I just thought about this kind of stuff. So I want to set the say spin chains and points of the okay. So the spin chains and then set the boundary with this filter. So it is completely open quantum system, but if we get the emergence of KPZ, so this will be nice. And I thought that okay, so if we really can map to the spin 1/2 example, and then we will see the emergence of KPZ. So this is a very naive expectation.
Oh, I see. Thank you.
I know, so this is kind of related to the first question a little bit. So the EXP model, I know that people come at unusual diffusion energy transport through EXP chain. That's where, since your boundary driven system might be nice to look at transport and transport if you study that role.
So I tried to compute the spin current on these spin chains, but I actually didn't know how to define the spin current because the quasi-particle here is not really like quasi-particles because there is no, how to say, the annihilation operators. So I said that the writer said the anchor state is not really the vacuum for the quasi-particle state. This is a problem. So I didn't know how to define the current here. So if you have any ideas, please let me know.
Okay. I have one last question maybe. So is it easy? How it's easy or difficult to prepare the initial condition in this space or particle?
Easy. You can say this is so here. So you can say the initial state is mean state. The difference is the choice of the total magnetization. If you set ST equal to some even numbers, there is no overlap with the specific towers. But if you choose the total magnetization is equal to some odd numbers, you will have overlap.
Okay. So if experimenters want to set this initial conditions, then
Which model this is? I'm sorry.
This is a resolutive spectrum. I don't follow open spectrum.
okay, let's check the speaker again.